What is a hum? Hum is this kind of sound, or this. This is a noise which adds to the normal sound, and of course we don't want to hear it. So let's see why this is sometimes produced and how we can avoid it. This is the schematics which I will utilize in order to show where the hum comes from and how we can avoid it. Here you can see a typical sound system which is composed on the left. If you look at on the bottom left, we have the source. This can be any analog source, such as, for example, CD player, analog output, or FM tuner, or whatever. Then we have the audio preamplifier. Then on the right we have the power amplifier. Each one of the two equipment, preamplifier and power amplifier, with its own integrated power supply module. Still looking at the picture on top left, you can see the power wall socket. Reported in green, you can see the signal path, the audio analog signal path from bottom left, the source, through the preamplifier. You can see the two preamplifying tubes. Going to the right, you can see the two power tubes. Finally, to the output transformer of the tube amplifier. Then I didn't report, but of course you have to imagine on the right we have the speakers. Typical power supply module, which is integrated into both preamplifier and power amplifier, provides at least two output. One is the high voltage for the tube's anode. This can be any voltage from, I would say, 200 volt to 500, even 500 volt for the power tubes. Another one is the heater. This can be either AC or DC voltage, much lower voltage, typically 6.3 volt for the tube's heater. Let's first see which are the potential sources of hum. Let's start from the wall power supply plug. Starting from the plug, we have the power cable. Then we have the power socket in each one of the two devices. And internally we have the cable feeding the 230 volt or 110 volt alternate current. This is the first potential source of hum. Every time, in fact, that an alternate current travels through the wire, this generates an electromagnetic field. This field propagates over the air. And this might be picked up by a nearby wire. In our case, this can be picked up by a nearby cable carrying audio signal. This is very important, and it's the basis of the electromagnetism and also the basis of radio propagation. And again, this is the sound of the potentially induced noise. Then we have the power transformer. Even the power transformer itself can radiate 50 Hz signal or 60 Hz according to the country to the outside environment. And again, this is the produced noise, the frequency being the same, 50 or 60 Hz. We will see later how we can shield the power transformer, how we can make the power transformer less prone to radiating 50 Hz or 60 Hz signals. As you see, we have a tube rectifier after the power transformer. The same is for a silicon rectifier as well. Things do not change. This is the waveform we see for the high voltage after the rectifier. Then we typically have a smoothing capacitor immediately after the rectifier. If you look at the voltage coming out from the smoothing capacitor, we can see this kind of ripple. This is an additional waveform on top of the nominal DC voltage. If we analyze a little bit this waveform, we see that it has a strong 100 Hz or 120 Hz component and then other higher frequencies components. So if we listen to the sound of this waveform, this is more or less like this. Still speaking about the power supply module, we have then other components which smooth the ripple further. For example, we can have a smoothing choke, and in fact we can see at the end that the waveform is the one more or less you can see here. As you can see, the ripple is much lower than the one we had before the smoothing choke. But again, also in this case, the sound of the waveform is the same and is more or less this one. So we have seen that all the components of the power supply module can generate hum, each one with its peculiar frequency and intensity, of course. But nevertheless, it's very important to carefully shield all the power supply components. What we have seen now is the high voltage part of the power supply module. We have another important part within the power supply module which feeds the tube's heaters. As we said before, the heaters can be fed with either alternate current or DC. In case of AC heating, so in case my power supply module provides AC voltage to the heaters, we have two kind of potential issues. The first one can be the hum picked up by the audio signal flowing through the tube itself. The tube's cathode are very close to the tube's heaters. So the current flowing through the tube's plate and the cathode can be impacted by hum, which can be magnetically picked up from the tube's heaters, thus impacting the audio signal. According to my experience, this is not an issue if the amplifier is properly laid out for all tubes handling line level signals. So if the signal does not go below, let's say, 500 millivolt, then again, according to my experience, I didn't find any issue due to hum induced by the tube's heaters. Second kind of issue is the magnetic field radiated by the wires feeding the 6.3 volt AC to the heaters. This is a very strong magnetic field which of course can impact the exposed areas of the amplifier where the audio signal is flowing. We will see later in the next video. In all my projects I utilize shielded cables for the wires feeding the AC heating to the tubes. Another potential cause of noise, of hum, is the ground loop. Ground loop occurs when each and every point within the amplifier has two different paths to ground. as we can see in this example. Let's consider in this picture the below reported power socket. We have the safety ground, of course, connected to the power socket. This ground connection goes into the chassis of the preamplifier in this case. There will be a connection between this ground socket and the chassis itself somewhere. Also, there will be a connection between this wire and the external shield of the cable connecting the preamplifier with the power amplifier. So let's now go inside the power amplifier. There will be again a ground connection. This ground will be then connected to the safety earth of another power cable, the one you see here. Then this power cable, in particular the ground cable within this 3 conductors cable, will go to the wall socket. And again there will be another ground connection on it. So we have understood that for each and every point within the preamplifier or the amplifier we have 2 different paths to ground. So we have what is called a ground loop, so a closed loop. This is not good because all the points belonging to the ground should have the same potential. So all those points should be at 0 volt. This is not completely true in this case because all cables, all shields belonging to the ground circuit do have some little bit of resistance. So any magnetic field I might have nearby, for example coming from power lines, can induce current flowing through the resistance of the ground cables. This might cause small AC voltage variations along the ground cables. And again, this might be heard as a hum. So in order to avoid this, we will see that in the next video, more in deep, we'll need to break the ground loop. One solution, for example, is to utilize shielded cables with just one end connected to the ground. Also, in order to avoid any ground loop inside the preamplifier or the power amplifier, it is highly advisable to implement a star grounding scheme. We will see that in the next video.